My area of research is Arctic climate change. And what I'll be talking about in this lecture is first a bit of a review of what have we seen in terms of changes in the sea ice cover in the Arctic. And then also, when do we expect the Arctic to become ice-free, and what are the mechanisms responsible for an ice-free Arctic? And what I want to specifically focus on in this lecture is three questions. Can we restore the sea ice in the Arctic Ocean? And if we can, what do we need to do in terms of our CO2 emission? And do we need to resort to sequestration or geoengineering? And finally, what are the timescales associated with the restoration of the sea ice? There's the political timescale, there's the technological timescale, because we're speaking of geoengineering and also sequestration, and there's the physical timescale associated with the climate system. One of the main misconceptions in the public is that there's a tipping point in the system. There's a point of no return. Once we pass that, once we lose the sea ice, we can never go back. This is one main misconception that I want to address. Basically, there are no tipping point in the climate system when it comes to sea ice. If we cut our emission of CO2, the sea ice will return.
Professor Tremblay's research focuses on high-latitude climate change with special emphasis on the future of sea ice cover in a warming world. His work focuses on modeling, analysis of global climate models and satellite data, and field work. Professor Tremblay has published more than 60 refereed scientific publications with more than 100 co-authors. He is involved in the Canadian Arctic Net Mooring Deployment Program and the Canadian Arctic Buoy Program. His research is funded by the Office of Naval Research, the United States National Science Foundation, the Canadian Natural Sciences and Engineering Research Council, and ArcticNet, among others. So at this point, it gives me great pleasure to introduce Professor Bruno Tremblay.
Thank you, John. Thanks for coming here tonight. When I usually give a talk about Arctic climate change, what I typically do is I talk about the observation. I talk about how the sea ice up there is really declining, especially the end of summer sea ice. For instance, we've lost about half of the summer sea ice area only in the last 30 years since we've been monitoring with satellite data. And basically, I explain a bit why is it that it's changing? The ice albedo feedback. The ice is a reflective media, it reflects the sunshine. The ocean is a very absorptive media, it absorbs the sunshine. There's a strong positive feedback that comes along with those two characteristics of the ice and the ocean. Talk about warm ocean current coming in and then triggering rapid ice decline. And then basically someone at the end asked me, so what can we do to reverse this? What can we do to change this? And then I say, well, we need to reduce our greenhouse gas emission. Okay, well, it's interesting to actually know what's happening up there. It's interesting why it's happening up there. But I think now we're ready for more pointy questions. I think now we're ready to move to the next step and really ask the question of, well, first of all, we will likely lose the sea ice cover in the summer in the Arctic in the next 2-3 decades. So can we bring the ice back in the Arctic Ocean? We keep hearing about tipping point in the news, points of no return. Basically, you cross some threshold and then you lose all of your ice and you can never come back. We keep hearing that on the news. Is this correct? Are there tipping point of no return in the climate system? Okay, these are the kind of questions that I want to answer. Also, what do we need to do if there are no tipping point? If we can bring the ice back, what do we need to do in terms of emissions? So yeah, we need to reduce our emission, but by how much? What do we need to do in terms of emission reduction? Is it something that we can achieve collectively, reduce those emissions to actually bring the sea ice back? Okay, and then the last but not least is the time scale. If tomorrow we reduce our emission, when will the ice come back? How many decades or years or centuries will it take before the ice comes back? These are all questions that I think now we're ready to answer, and we basically have climate models that we're using to actually answer those questions, and this is really what I want to discuss here today. Can we restore the sea ice in the Arctic? So these are the questions that I just mentioned. Can we restore sea ice in the Arctic, or are there tipping points in the climate system? What do we need to do to restore the sea ice, and what are the timescales associated with this restoration? And I'm going to give you the answer right away. So we're not going to keep wondering, and I don't want to have suspense. I'll tell you exactly what the answer is, And then we're going to spend the next hour like actually focusing on why, how do we come to this conclusion? And we can just like have our brain fully attention to why is this happening. Sorry for the blue here, it doesn't show as well. But yes, we can restore sea ice. There are no tipping point in the Arctic Ocean, in the sea ice cover. You see those kind of behavior where you have like constant forcing, constant CO2, and maybe you have like two equilibrium state. Well, you see that in very simple dynamical system. When you add complexity to your model, basically you lose those kind of behavior. So there are no tipping point. We can restore sea ice. It's all a function of the CO2 concentration in the atmosphere. What do we need to do to restore the sea ice? Well, CO2 emission. We actually need to bring CO2 emission back to a pre-industrial value within 30 to 40 years. This is quite challenging. If you want to maintain sea ice according to climate model, which participated in the last IPCC report, this is what you need to do. So you're going to be saying to me, well, Bruno, like, why do you bother? But then, okay, and which brings me to my point, which is like maybe we need like an engineering solution, or maybe we need sequestration solution. I'm going to be discussing those as well. Scientists are not very warm about engineering solution to this problem. Sequestration might be a little bit more like scientists are more at ease with this, but I'm going to be talking about what it means and basically like how we go about this. What are the restoration timescale with this restoration? Well, several decades. There's political timescale. There's technological timescale. I just mentioned engineering solution, technology, and there's also the physical timescale. Political timescale is that if today all of you decide, yeah, this is an issue, we need to do something, it takes a while before the political machinery gets into motion, a decade or so. Basically, then there's the technological solution. Now you need to invest in those technology to actually sequester carbon or do something to actually help reduce the CO2 into the atmosphere. Those will take, again, a few decades. And then the physical timescale, which is, okay, now once you've done all this, how long will it take for the system to react? And those are a couple more timescales. So, and this brings an interesting, so when we talk about like, we're talking about like 50 to 100 year timescale before we can actually achieve those things. So different stakeholders up in the Arctic have different interests. Like an oil company, a shipping company might be very happy to see the ice disappear because it's more like places where they can drill for oil. A shipping industry, like it's going to cut their transit time by half to go from Europe to Asia. That's pretty good. Local Inuit people might not be so keen because like it's, when you talk to Inuit people, like they talk about the sea ice as the land. They say like when we go out on the land, what they mean is that when we go out on the land fast ice, basically, like the ice for them is the land. This is where they hunt. This is where they fish, like for seals and polar bear. And basically, losing the ice means losing their fishing ground, their hunting ground. This is not good. But wait a minute now, like we're talking about maybe 50 to 100 years. So we're talking 3-4 generations of Inuit people who will have seen no ice in the summer, who will have seen the tourism industry like come up, who will have seen like a petroleum industry, mining industry, who will have seen the warmer climate in the summer, an economy that might have been like more active than it is today. Will even the Inuit in 4 generations like want to see the ice return like in 100 years? Maybe even the local people will not want to see that happening. So these are interesting questions that I had not thought about personally before answering to this project, but these are the kind of ethical questions that we're talking about here. Okay, so, and maybe like I want to say, you might be wondering like, well, who cares, like the sea ice, like there's just like 100,000 people living up there and then sea ice, polar bear, seals, okay, we're gonna lose those, and so what? At our latitude, we're not gonna be affected. Yes, it is true. But basically, like what I'm going to be arguing here, today, is that the Arctic is like the canary in the coal mine. So we're warming the globe. What's happening in the Arctic is happening like several decades earlier than what's going to happen at lower latitude. So basically, at lower latitude, it's going to affect much more people. We're talking about an expansion of the Hadley cell that John talked about in his seminar last time, which means like more drier tropics, which is the location where poorer countries are located, and they have less means to actually manage those kinds of shortage of water. Okay, we're talking about sea level rise that's going to have an impact on lower latitude on a lot of people. So while in the Arctic there are less people, we believe that it's really a test bed, because to solve this problem in the Arctic, you need to bring countries together, mainly the countries that have borders around the Arctic Ocean. So if we can bring those countries together and iron out like the kind of problem that you have in negotiating and finding solution to this kind of problem, we will be better equipped to actually deal with the larger problem. And larger just because it will affect more people, because the people of the north will be very much affected by these changes. But basically, we're talking about now we might be better equipped to actually tackle a problem that's going to happen at lower latitude, okay? And we will have had an experience of working together and trying to find solution. Okay, so this is why we organized like a workshop. Like in 2012, I was on sabbatical. I was at Columbia, and then we basically like organized the workshop there. And what we did is we brought together politicians, engineers, scientists to discuss these issues of restoration of sea ice. Politicians because we need to understand the political timescale. Engineers because you're going to see later we will likely need sequestration. Hopefully not geoengineering, but we will likely need some solution like this. And basically scientists because we're talking about climate change and we're talking about restoring the sea ice. Okay, so this is, we brought all of these people together. If we were to redo this thing, and we plan on redoing it, like again with my colleagues like down in New York, I would argue we should bring also historians, and we should maybe bring social psychologists. We need to broaden the field here because, I mean, we've done our work, like, I mean, the signal is clear, climate is changing, and yet people are not yet convinced. So it's got nothing to do with the fact, with the observation, it's got to do with something else. It's political, it's ideological. And maybe the question is, why bring social scientists, why bring maybe like historian? There were in the past, like paradigm shift that occurred in the past. And these take time, and what is it that makes those big, large change in opinion happen in a society? So, and it would be nice to hear their perspective, because now I think we're ready for that. Like, I mean, clearly, like, I can repeat, like, about climate change, about sea ice, about CO2. I mean, I can repeat it all I want. It's not having an impact on people's opinion. We need to actually broaden the field of view, and maybe social psychologists, like, what makes people so resistant to changes? And why are people, like, so reluctant to actually change their value and take action based on evidence that is not 100% sure, but sure enough that you need to do something about it. Okay, so this is my introduction. So there has been large changes in the Arctic in the sea ice cover. Like since the late 70s, this is when we started to monitor the sea ice on a daily basis. We have polar orbiting satellite rotating around the Earth is rotating underneath it, and basically since 1979, those polar orbiting satellites will pass 23 times above the Earth's surface every day. So we have a complete coverage of what's happening in the Arctic day by day by day for the last 30, 40 years. And this is what's happening. Sorry. So on the top left here, 1979, what you see here in purple is the line, it's the mean ice extent at the end of the summer. Okay, and the mean taken over the 80s and the 90s, for example. So what you see in white is the actual sea ice extent, and what you see in purple is the mean sea ice extent for those 2 decades. So in 79 here, what you see is that you're slightly above average. In 84, 5 years later, again, you're slightly above average. In 89, you're pretty much very close to the mean. In 94, again, you're a bit above average. And in 99, you're a bit lower in places and more in others. And in 2004, again, nothing much happening, a slight decline. So you can see that for the longest time, all the way from 79 to 2004, there was a decline, but it was a pretty mild, like small decline. And then 2005, 2007, and 2012 hit. 2007 is on the lower left, and 2012 here is on the lower right. Basically, in 2012, we had half of the sea ice extent at the end of the summer compared to the long-term mean in the 80s and the 90s. We had lost half of the surface extent covered by sea ice. And if we were to show like data about like the volume, we had lost 75% of the sea ice volume. Area is very misleading. You can have like a thin ice cover like this covering the entire Arctic. The sun wakes up one morning, melts this in one day because it's very thin. The thickness of the ice is really what counts, but we have less data about this. But we have reason to believe that the sea ice volume decline is even larger, of the order of 75%. Okay, so this is the kind of system that we're dealing with now. And large changes occur, like in the 2007. Basically, it's a preconditioning. What's happened is that in those 2 decades where I see not very much changes, there were changes. There were changes in the thickness of the sea ice. Okay? And basically what you do is you thin the ice, you thin the ice, you thin the ice, and then there's a warmer year. There's natural variability in the system. But now the warmer year onto a sea ice which has been preconditioned and thinned will have much larger impact than on the thicker sea ice cover. You start opening up the pack, then you have open water absorbs the sunshine, absorption of solar energy, then create more melt, and then you have the whole ice albedo feedback kicking in. And then frankly, there's other feedback. Once you have open water, the atmosphere warms above it, and you no longer have ice cloud in the Arctic. What you have is liquid water cloud. Ice cloud lets the long wave from the Earth just go through, and it doesn't really interfere. Liquid water cloud has a huge greenhouse effect. You might have experienced that going camping in the fall when you have a clear blue sky during the day. The nights are extremely cold because the Earth is cooling off. Nothing is preventing this from happening. But if it's a nice cloudy day, well, the Earth is trying to cool off, and those liquid water cloud absorbs the long wave, re-emits it down, keeps the surface warm. So ice albedo feedback is a big feedback, but also the cloud phase change is also a big feedback explaining the kind of change we're seeing up there. So this is the background. And this gives you an idea of what the sea ice extent change. This is basically the minimum sea ice extent in September, okay, from the 1979, which is at the beginning of the satellite era. And you can see here, if I drew a line in the first part of this record, there's a very, very, very gentle decline. But you can see starting in 2005, 2007, 2012, the decline has really, really accelerated. And now we're entering a phase of like rapid decline, the very same rapid decline that our model was predicting to happen in one of the articles that some of you have read. Okay? So this is basically the data, satellite data. For the future, though, we want to talk about restoration strategy. So we want to talk about the future. We will use model. Okay? And basically, this is the exact same image, sea ice extent and time on the bottom axis. And this one will go from, this is around 1980 all the way to 2100. This is one of the model, one of the GCM that we're using to study those kind of questions. If I had put all of the GCM, all of the possible ensemble member, basically it would be a very cluttery picture, but they will show like a very similar image. What we see here is from the community Earth system model, which is developed in Boulder, Colorado. Yes. Okay, so basically in blue, what you see is the different ensemble member. When we run those models, we don't just run one simulation, we run many simulations, because if you change the initial condition by 0.000001 degree somewhere in Africa, in 100 years, in a few weeks, and then in 100 years, you're going to have a different simulation. And these different simulation is all of those green lines there, and basically it gives you an idea of the natural variability in the system. And then when you look at the mean, what this gives you is basically the force variability, because this is common to all. And what do I mean by forced? Well, it's the one that's forced by CO2, basically. You put greenhouse gas in the atmosphere, more long wave down, and this is the force response. So by looking at this image, we have an idea of the force response in black, and the cloudiness of the blue lines around the black line is basically an idea of the natural variability in the system. And you can see that like the natural variability is quite important. Like in some simulation, you lose the sea ice in 2 decades, and in some other simulation, you lose them in 4 decades. There's about a 30-year window by which we cannot be more precise. I can tell you we're going to lose the sea ice within 30 years, starting in 2030 all the way up to 2050, 2060. This is as good as I'll ever get. I cannot go any more than this because the rest, the uncertainty is natural variability. We cannot predict natural variability. This is a chaotic system. This is like predicting weather in 5 days. We cannot do it. Okay? In red there is the satellite observation. So you can see, I wish I had thickened my line, and I had made a note for myself there, thicken the line, sorry about that. But I wanted to make my line a tiny little bit like thicker, and this is the observation that I showed from the satellite in the previous image. And you can see that some of the ensemble member, okay, reproduce the observed decline, okay, and basically some of them are a little more sluggish. Is that bad? Is this good? Well, we don't know, because we're on a path. It's only one realization. The reality here is only one realization. Are we around the mean? Are we like a realization that's kind of an extreme pessimistic and extreme optimistic? We don't know. Okay, we have to live with this uncertainty. We don't really know this realization that we're going through altogether. If we were to go back 100 years and change a tiny little bit, like one temperature somewhere, we would have a different realization. Will it be less extreme than the one we're experiencing now? Will it be more extreme? We don't know. Okay? But the bottom line is that this red line is within the envelope of the blue line, and it gives us confidence to use those models to actually make projection into the future. So on this panel, we had a politician, and this guy was Rafe Pomerantz, and he was the assistant deputy minister in the Clinton administration for the environment. And he told us, like when we started, he was on the committee, or the organizing committee, and he told us, look, like if you want to sell this to politicians, you need to talk about the services that the Arctic is providing. They want to know what service they get for what money they're going to be investing. That's the way politician works. So we kind of I'm framing this article and also like this talk today in terms of what are the services that the Arctic is providing for us locally and for us globally. Okay, so I'm talking about local services and global services. Local services, well, habitat, polar bear, seals. On the top left here, what you see like is algae underneath sea ice, which is the basis of the ecosystem there. And what you see on the bottom left here is Arctic cod. So basically, there's a whole ecosystem around the sea ice. And there's animals that are designed to actually work from this like hunting base. And so basically, this is one service. If you lose the sea ice, you lose those habitat. Subsistence hunting, Inuit health. These are, again, local services. Inuit, more and more they will eat food from the south, but basically like the traditional food, like polar bear, seal meat, and things like this, and fish, it constitutes about 20-30% of their feeding habit, but it constitutes about 80% of the nutritional input that they take. So it's a relatively smaller percentage of their total food, but it's a significant percentage in terms of like vitamins, nutrients, and things that they actually need to actually be healthy. So again, if you lose the sea ice, you lose this service. National security. I don't know, some of you might have followed the news, but there was a Russian flag being planted in the North Pole. What I'm showing here is a map of the Arctic Ocean. And basically, I'm talking about national security here in the context of the law of the sea says every country is allowed 200 nautical miles away from their shore or the edge of the continental shelf, whichever is farthest. Okay? So if the Russian here can demonstrate that this Lomonosov Ridge in the middle of the Arctic here is an extension of their continental shelf, basically they can claim all the way here, they can claim this region here of the Arctic for natural resources, for petroleum, and for all of these things, all the way to north of Canada and Greenland. And geologically speaking, look at the shape of this thing. This thing, millions of years ago, was actually out on the edge of the shelf. And then there was a spreading ridge underneath. And basically, like the plate started to move apart. And this spreading ridge, you actually see it here, and I'm showing it on the next. This is the Gackle Ridge. This is the extension of the Mid-Atlantic Ridge, which goes all the way into the Arctic Ocean. This is giving you like new crust. And it's pushing the Lomonosov Ridge away from the Eurasian coastline, but nevertheless, the Lomonosov Ridge was part of the Eurasian coastline. And the Russian assertion that this is an extension of our continental shelf is correct. The Danes are trying to say, no, this is an extension of our shelf here. And the Canadians are saying the same thing. They both know that they have no chance. They just do it to stall the project, to stall the prospect of like the Russian actually acquiring this. But the Canada and Denmark, this is not going to happen. We're not going to have these kind of land here. But maybe even the Russian would have a difficulty getting it, simply because right here at the edge there, there's a little rift, and basically the connection with the continental shelf is not like entirely clear. And they need to show basically like there's a connection between the two. And this is where we are now, like when they submitted their latest proposal to the law of the sea, this is the kind of science that they need to provide to actually convince people that they are allowed to extract the resources along the Lomonosov Ridge. So in a sense, it's kind of childish, but at the same time, it did something good, is that it forced Canada, Denmark, US to actually map their coastline and do research work there, because doing that could extend their shelf and could actually give them access to more natural resources. So a lot of science has taken place in the Arctic just as a result of being able to grab a bit more of the land. And this is basically this is what the Russians are claiming here. This is the line here is the 200-mile limit, and now they want to extend all the way up here, and this is the new region that they want to acquire as part of their continental shelf. So global services now. Well, global services, the sea ice is like a mirror. It reflects the sunshine, keeps the planet cool. Without the sea ice, we'd be half a degree warmer, potentially. So it's a good thing, especially in the prospect of global warming. Basically, sea ice, if you lose it, you're going to have a half degree more temperature to deal with. And we're talking about, I don't know if you followed like the Danish Copenhagen summit. People are talking about a target of 2 degrees Celsius, 350 part per million of CO2 in the atmosphere. Well, basically, half a degree is not insignificant compared to the 2-degree target. Here, the ocean circulation, you may have all heard like the global thermal line circulation. This is basically like water from like the Gulf Stream off of the coast of the States, like breaking off at Cape Hatteras, moving towards Europe. And then as it goes northward, it gets colder and colder and colder, and cold water is heavier. And it comes in the Greenland Sea, it's so heavy it sinks at depth. And it comes at depth, and then there's a global thermal line circulation like this. This brings heat to the north, keeps Europe warm. If you start melting the sea ice up there, well, you're bringing fresh water up there. And fresh water is very light because it's not salty. And so basically, while the water are very cold, when they go north, they get heavier, but when you mix them with fresh water, they become very light. It's like oil sitting on top of water. You cut the convection, you cut the global thermal line circulation, and basically you can actually have a potential impact on European climate. So melting sea ice, 3 meters of ice over 10 million square kilometers over the next 30 years, that's not going to do it. But melting Greenland, which is just south, because if you melt the Arctic, you're warming up this region, and Greenland, which is just next door, will experience warmer weather. And basically you will increase melting over Greenland. And Greenland is land ice. It's ice that sits on rock. When you melt, the fresh water goes into the ocean. It constitutes sea level rise, and it also can stop convection. So if you were to melt Greenland in 800 years, the entire Greenland, you could stop the thermal line circulation. It could have an impact on climate in Europe. But our climate model, as of now, do not have dynamics of ice sheet like Greenland, so we're not projecting that far into the future. Another service of the Arctic, release of stored carbon. If the Arctic is warming up, the permafrost on the land, you see here a map of the permafrost on the top right. This is everywhere you see blue, this is where we have permafrost, permanent or like a not broken permafrost. If you warm up the Arctic, you warm up this region, you warm up the land. If you warm up the land, you melt the permafrost. Okay? There's a lot of stored carbon in the permafrost. There's a lot of like organic material, and that will be released to the atmosphere. It's going to be a new source of CO2. It's very hard to quantify. Maybe like someone here will be talking about release of carbon from land, but this is another service that the ice is providing for us. It keeps the Arctic cooled, it keeps the permafrost cold, it keeps the carbon in the organic matter locked in ice in the soil. Another service. Extreme weather, I think John spoke about this. With CO2 in the atmosphere, what we're seeing is polar amplification. The warming in the Arctic is larger than the warming at the equator. And this is just because of this ice albedo feedback. You transform a region which was continental climate because you have ice into a region which is maritime climate, which is very mild because now you have ocean. So you reduce the temperature gradient between the equator and the pole. And this temperature gradient is basically the speed at which weather pattern at our latitude travels from west to east is basically a function of this temperature gradient. And when you reduce the temperature gradient, those weather pattern migrates from west to east more slowly. Sometimes so much that they're actually stationary. We call them blocking highs. And then what you have is like a rainy day that just lasts forever, or a dry day that lasts forever. It leads to extreme weather. This is one mechanism by which you can have extreme weather. So basically, warming of the Arctic is actually one potential cause for extreme weather, simply because of those blocking patterns. And I'm giving 2 examples there. Sea level rise, this is another service. Well, the Arctic sea ice sits in the ocean. This is like you, when you take a drink and you have an ice cube in your drink. When your ice cube melts, your drink doesn't start, the level of water in your drink is not rising, because your ice cube is already displacing a certain volume, and it just fills that little volume. So you lose sea ice, you're not changing the sea level rise. But you're warming up the Arctic, and just south of there is Greenland. And Greenland is land ice, and you increase melt over Greenland, and then indirectly you affect sea level rise. Okay? And this is just like it's actually a slide that I took from a climate skeptic website. So I love using climate skeptic like material to actually promote the climate case. But anyway, this is basically like images of where the sea level will be in 2050, 2030. And it's just not like the sea level is rising and then you're going to be flooded. It's more complex than this. When the sea level is rising, the probability of you being flooded increase because what if you have high tides? What if you have a storm during high tides on a sea level which is higher? Then you're more likely to be flooded. So it's not like one day you're going to be fine and the next day you're going to be underwater. It's more that the probability of being flooded as time moves on will increase. Okay, and you've seen that, like Sandy in New York. I mean, there was a blocking high at that time. Like this storm just stayed out there. It wouldn't have been that big of a deal if it just kept going towards Europe. But it stayed there. It stayed there. The wind blew the water against the coastline. The sea level was rising, just mechanical pushing. You just blow on the water against the coastline. And with consistent wind, because there was a blocking pattern at that time. And basically, like you had a flooding, and there was also like a storm, like just a month ago, I think, like again in the New Jersey shore, and again there was large flooding. You will see that happening more and more often. Like in New York now, like I had friends which lives like just in Brooklyn, like and their area was reclassified for insurance purposes. So now they're considered a region of high risk. So their insurance premium have gone up. So after the Sandy storm, they had to rebuild. Not only they had to rebuild, but they had to rebuild on stilt, and their insurance premium has gone up. So basically, we're talking about real impact on real people here. And this is just like the beginning. We're going to see that more and more and more. And it's not just that, it's also pollution sometimes of salinization of like groundwater. When the sea level is rising, basically the gradient between your fresh groundwater and the ocean changes direction. It's the salty ocean that actually migrates into your aquifer. Now you have to build like desalinization plant before you can drink your water. So we're going to see that happening in Florida. We're already starting to see that happening in Long Island, but to be fair, they've been overusing their groundwater in Long Island. So they've been lowering, and then the gradient is going the other way. But as the sea level is rising, this is just going to happen more often. Interest in the blue Arctic? Well, resources extraction, like oil. Some companies have already bought the rights to actually explore, like in the Beaufort Sea of the Arctic, north of Alaska and Yukon. Shipping. I said before, like to go from Europe all the way to Asia, like you cut half of your distance if the sea ice in the Arctic is actually retreating. So this is quite a bit like of saving in terms of petroleum that you need to use for propelling those ships. What people are talking about now is when you talk to the shipping company, they're talking about having a base here on Svalbard and another base here on an island there in the North Pacific. And people would just come with their cargo, and then they would just go like straight towards North Pole with ice-reinforced vessel, and then carry the load and then dump it onto another normal vessel on the other side. The reason why they don't want to go here where the ice is much more open is because when you go in Russian water, you basically need to have an escort, even if there's no ice, even if there's no potential for like accident, you need a Russian icebreaker. And a Russian icebreaker is $100,000 a day operation cost. So basically, like you're cutting your costs a lot if you don't go into Russian water, except that if Russia win their claim with a lot of Lomonosov Ridge, even going straight through North Pole in the middle of the Arctic, you would have to go through Russian water. It'd be really, really interesting to see like how this will play out. Fishing, well, less ice, then you're actually, your fishing ground is larger, so you have more places where you can go fishing. So this is like one of the interests in the blue Arctic. And tourism, this is a little extreme. Like nobody sunbathe up there. Although I've seen someone like swimming in these water like once. But just to give you an example, I was giving a talk to the Alumni Association of Canada, and we were like in the Northwest Passage, and we stopped in Beechy Island when the Franklin lost his first man. And this is kind of a touristic site up there. And when we arrived, there was one ship waiting to actually disembark, and there was one ship that was there already that was about to depart. 3 ships at one touristic site. Basically, like we were, it was like a, it was traffic jam, like at this location. The melting is like the season is only a month and a half, but it's intense. Once we have this month and a half, there's a lot of ship going there. French ship, Finnish ship, Russian ship, like American ship, they all go there like for tourism. So this is certainly like one interest in the blue Arctic. Okay, so in the introduction I said to you guys, like we're gonna need to think about CO2 emission and CO2 reduction. So, and then, well, is it realistic? Like sometimes we're thinking, well, the emission keeps increasing. Can we reasonably think that we can reduce our emission? Well, we can. This is the global, this is the total CO2 emission by country, and this is China here, and it just surpassed the US here in 2006. This is the US. You see here we're reducing the emission, but nothing to do with a will to actually reduce your emission. That's to do with 2008 economic crash. So basically the economy went down. The Russian here have been on a steady decline since 1989, but that's nothing to do with a will to reduce your emission. It's the breakdown of the Berlin Wall. But look at my next slide here. This is Sweden. Since 1970, Sweden has decreased their emission by half with technology that exists today. So basically, you can build buildings that are basically almost self-sufficient in terms of energy. If you orient them correctly with the sun, there's all kinds of like new way of building that can actually achieve this goal. Just like a warming up building and those kind of like infrastructure, this is 40% of our greenhouse gas emission. So if you go with like just like a building code, just like what they're implementing now in Germany, you can cut half of your emission like right there. It's very simple. The other half, well, is transportation. If you have like more like a public transportation, trains, things like this, well, electrical car, basically like there's a lot of potential for reduction. Like Sweden, I haven't heard of like them like going out of their way to actually get those reduction into the work, but maybe I haven't been following close enough. But basically, they've reduced their emission by half simply since the last 30 years. This is the emission per capita, and then you see Canada and the US are quite close. We're a very small population. This is why our total emission is so small. But nevertheless, what's a bit troubling is that when you look at China down here, okay, they have a big rise, and you see they're much lower than what we consume here per capita. So basically, there's a lot of potential for them to consume a lot more, and there are a lot more people. So you're seeing me coming here, like basically, we need to collaborate. We need to share technologies. They have a lot of power plants that they design, that they build. They're all based on coal. This is really like not very efficient in terms of like CO2 emission. Basically, there's going to need to be like a different mentality of like basically sharing technology. And because what's happening in China is also affecting us. If we can help them reduce their emission, we're helping ourselves. Sounds selfish, but it seems like it's the only way to make anyone move. You need to go with like, what's in it for me? And this is just like a population growth, just to give you like the previous slide, like which is like a per capita times the population growth, gives you like the total production. Okay, so we're talking about like we're going to need to cut like our emission. Let's say where are we in terms of CO2 concentration in the atmosphere, like and where were we in the past? Well, this is where we are. This is a time series from Mauna Loa, starting in 1950, 1960. I don't have my glasses, sorry. And then all the way up to today. We are at 400 roughly part per million of CO2 in our atmosphere, okay? This is where we are now. Okay, so historically, like what kind of level were we at and where do we want to go? Like where was it, like pre-industrial? What does pre-industrial mean? Well, when we want to go farther back in time, what we do is we can core in Antarctica, for example. We do a core and we take the ice out, and when you look at the ice, it's kind of whitish. You know, like in your freezer when you have ice, it's white. Those are air bubble. So basically, when the snow falls on Antarctica, more and more falls, then it sinks deeper and deeper and deeper, and the snow turns into ice. And the air at that time when it formed is trapped in those bubbles. So basically, you take slices of your ice core all the way to the bottom, and you can go back 800,000 years. Okay, this is how old the ice is at the base of Antarctica. and you cut slices, you look at the bubble, you vent those bubbles, and like you actually look at the CO2 concentration in those bubbles. And you know exactly how much CO2 there were in our planet for 800,000 years. This is not bad. And what do we see? Well, this one is Vostok. Dome C is 800,000 years. Vostok is only 400,000 years. But basically, what you see here is the CO2 concentration from today. And then this is like the pre-industrial, around 280 part per million. This like sharp line, sharp vertical line, is basically like the sharp increase that we've been seeing since the pre-industrial all the way to today. From 280 all the way to around 400 now. Okay? And before it was going from 280 to 200 to 280 to 200 with the glacial cycle. These are like interglacials, these are glacial time. And basically it's clockwork. For the last million or two, we've been going clockwork, 80,000 years of cold climate, glacial climate, 20,000 years of interglacials. So basically, an interglacial normal CO2 level is 280. Sorry. We can go even farther back in time. Look at this now. Like we're 0 here, and we're 20 million years before present here on the left side of my graph. 20 million years. This is like the 400,000 years of Vostok that is all squished to the right because this is the first 400,000 years of my time series. And the red here is the last 100 or 150 years that we've been measuring. If we go back to 20 million years, and how do we do this? Well, now we cannot go in ice core anymore because the ice is never as old as this. We look at boron isotope and alkanon, basically carbon isotope and boron isotope in the shell of little organism that lives, fall at the bottom of the ocean. You do a core at the bottom of the ocean, and it turns out that those isotopic ratio from carbon 13 to carbon 12 to carbon 14, from boron 10 to 11 to 12, those ratio change with acidity of the ocean. Acidity of the ocean is a function of the CO2 in the atmosphere. We can backtrack CO2 because of those alkanon and those carbon isotopic measurements. And when you go like as far back as 20 million years, you're still not at 400 like today. And then when you go back 60 million years, well, now here you are. Now you're entering the time of the Cretaceous. This is 60 million years ago when you had dinosaur, when the Arctic Ocean was basically very luscious, sequoia tree on Ellesmere Island, alligator remains like on Ellesmere Island, 20 degrees C, like in the mean climate, like in the Arctic. The Arctic was not that far, not much different location than it is today. So basically, like it was a very luscious climate in the Arctic, like 60 million years ago. And the CO2, we believe, was many, many, many thousands part per million. Now we're at 400, okay? And basically, you need to go 20 million years or more to actually see those kind of CO2 level. So people tell me, well, okay, we've been there, like even worse, like we've been at 2,000 like part per million, like a few million years ago. What's your problem? Well, my problem is that we've done this journey in 60 million years. Now we're doing the journey back in 300 years. If you're an organism and you want to adapt to those kind of changes, good luck, because 60 million years, you had plenty of time, you know, to adapt. 300 years, it's all more difficult. This is a picture from an artist of what the Arctic could have looked like Ellesmere Island, what it could have looked like 60 million years ago. We can go even further back in time. I don't want to dwell on this, but basically you can look at fossilized leaves in rocks, and you can count the density of stomata on the leaf. And when you are in a CO2-rich atmosphere, you need very little stomata to actually suck it up and then live. When you have in a very CO2-deprived atmosphere, you need a lot of stomata. And from the density of stomata on fossilized leaf, you can actually go even further back in time and tell what the CO2 level must have been even past like the 400 million years that I've shown you. And this is just one example, but I don't want to go and dwell on this thing. Okay, so it gives you now like a context of like where we are and where we want to go. Okay, so 350 ppm, the magic number, 202 degrees C, like where are those numbers coming from? Like there's not one day in the news during the convention, like in Denmark, in Copenhagen, where you didn't hear those words. Well, why? Why 350? Why 2 degrees Celsius? Like what's so magic about this, and why do we think that we can live with this? Well, what we do is, this is an ocean core. And what we find from this ocean core is, again, like delta O18. It's like a oxygen 16, 17, 18 ratio of those isotopes gives you a measure of the temperature at the time. So we take core in the ocean, we go back in time, and we measure what the temperature must have been during those times. We're going here, okay, from today on the far right, okay, all the way to the left, which is, well, this is many interglacial cycles, so it's about 500,000 years, okay, about 500, 600 thousand years. Okay, so in the past, there were other interglacials. We are now in an interglacial, but 120,000 years ago, we were in an interglacial. That one, you see, it's the first one that you see here, okay, was a little warmer than the one today. The one before was actually a little colder. The one before was a little colder, and then 4 before was actually much warmer. So we have experience. We've seen interglacial, and some of them, just by chance, just because of solar forcing, were warmer than the one of today. So, and when we look at sea level rise, like paleo sea level rise, we have other proxy for that. In here, we lost about 6-7 meters. We don't want to deal with this. But in here, we had about 1 meter, 1.5 meters of sea level rise, a 2 degrees C warming, and basically, this is where the 350 and the 2 degrees C comes to us, is that in the past, we have had interglacial that were 2 degrees C warmer. The southern tip of Greenland did melt, the sea level did rise, but it rose in such a way that we feel we can manage it. And so these are where those targets come from. 350, 2 degrees C. It's from just looking at past climate change from ocean cores. Okay, and this is now like basically my talk, which is about the sea ice. So now I'm back to the GCM. We're looking at global climate model, and we're going to look at what will be the sea ice in the future, depending on the emission of CO2 scenario. Okay, so here I'm showing you many different scenarios. These are observed CO2 level, observed emission level, and now the RCP 8.5 is this red line here. This is like business as usual, okay? So basically the CO2 emission keeps increasing, and in 2100, well, you kind of run out of fossil fuel and then you level. The RCP 6.5, well, you let it increase, and then you take action near the end of the century, and then it's stabilized here at a lower level. And then here in the RCP 4.5, well, you increase, and then you take earlier measure and you reduce your emission to this level here, okay, which is higher than pre-industrial. And the 2.4 here, you take action immediately and you reduce your emission to pre-industrial level. These, we don't know what we're going to do about CO2. I mean, chances are we're going to be on the red curve for a while, but basically we don't know, so we try everything that we can, and we see like this is an envelope of possibilities that we may be considering. So what will happen to the sea ice if you run your sea ice model with those kind of emissions? Basically, when you do this, these are the corresponding CO2 concentration in the atmosphere with those emissions that I've shown you before. If you do the RCP 8.5, you will stabilize at 2,600 part per million. If you do the RCP 6.5, you have 800 part per million, 4.5, 550, and then the RCP 2.5, you're going to have 350 part per million. This is the famous 350 here that like Jim Hansen and all of these people say we should be shooting for. Okay? But look, like to have 350, what does it mean? Look at my previous slide. It means we need to bring back the emission to pre-industrial level and start acting now. It's pretty aggressive. This is to reach Jim Hansen's from NASA GISS, and you know, like 350.org, and if you read those like those news agency, but basically this is what you need to do. Bring the CO2 emission to pre-industrial and start now, and bring them down to pre-industrial by around 2080 or something. So what is the sea ice doing when you do that? Well, in black, what you see is the observation that I showed you at the beginning of my talk. Okay, and this is climate model projection in different colors. So if you look at the red curve here, this is the RCP 8.5. This is the one business as usual. So business as usual, the sea ice goes down to 0. It basically means you have an ice-free Arctic. You have lost your sea ice cover. If you go with the RCP 4.5 or 6, which were also pretty aggressive, basically you're left with about 1 million square kilometers of sea ice, and this is what the Arctic would look like. Basically a bit of ice north of the archipelago, a bit of ice in the archipelago, but for all practical purposes, we call this a seasonally ice-free Arctic. okay? And if you want to maintain a sea ice cover in the Arctic, if you use RCP 2.5, which is the most aggressive in terms of CO2 reduction, what you get is sea ice level similar to what we've seen in 2012, 2007, that we think of as very retreated. Well, if we did that very aggressive scenario, we would kind of settle around that kind of ice, okay? There would be ice in the Arctic. There would be enough for polar bear to survive, for local Inuit to have their traditional food and everything. So basically, if you want to maintain the sea ice cover, it's basically the same target as what Jim Hansen has suggested we do in order to avoid tragic climate change associated with drought in the subtropics, sea level rise. Basically, the target to maintain sea ice in the Arctic is the same target as for those other considerations. 350 parts per million, and bring the emission down to pre-industrial within the next 60 to 80 years. Okay, so this is what I just said. Well, can we do this? I mean, Norway reduced their emission by half in 30 years. That's not enough. Even if everybody did that, that's not enough. We will likely need means to actually eliminate CO2 from the atmosphere. And those that we are considering now are, the one that I find maybe the most plausible at this point is carbon dioxide reduction, which is emission reduction and carbon capture and sequestration. What we mean by sequestration is that you strip the CO2 out of the atmosphere. You turn it into calcium carbonate, the white stuff that you see inside like oysters. You basically transform it into a solid, and then you bury it in a mine, and then you hope that they're stable down there and that they're going to stay there in the solid form. A lot of universities in the world are actually doing experiments where they shoot CO2 into the rock and they see how stable it is and how much we can store in there. So this is research that needs to be done, and there's not enough of this research that's being done, but basically, if we're going to need to go there, we're going to need to invest more heavily in those kind of research. This is what it could look like. You see here those big fans on the left. Well, these are big fans that suck the air up, strip the CO2, and form calcium carbonate, and then you would dump this into an old mine and hope for the best. You would have to power this not with fossil fuel, but with wind power, which is what I'm showing on the right. And basically what you have is a mechanism by which you can reduce CO2. We're not talking about continuing to consume business as usual. We're talking about we do everything we can to bring our, to use alternative energy source, to use better buildings, better insulation, less CO2 emission. And then even when you do all this, there will be a need for a little kick in the system, and you might want to use those technology just to help you out, and then after you do without, and then you ride the wave, and then you can get out of this. This is kind of where we are located now in terms of our thinking. Other strategies, which I disagree with personally, is the solar radiation management, which is geoengineering. Some people have talked about more reflective crop, so basically use Boston lettuce instead of kale, because it's lighter green, so it reflects more sunshine. I don't know how much it's going to help us. We're talking about reflecting roof here, white roof to reflect solar radiation from buildings. Montreal has already adopted a law like this. And if you build now a new roof on top of your house, you will need to use a white roof or white little rock onto your roof. So that's one mechanism by which, but there's only so much surface area that houses occupies on Earth. It's a small thing. People are talking about sending satellite up there with huge mirror, and then you can deploy the mirror and change their angle and then reflect solar radiation and monitor our climate. But some people have seen that similar to what happens when you have a volcanic eruption. You basically have sulfate aerosol all the way to the stratosphere. They form cirrus cloud. They make the planet more reflective. Yes, and then they cool the planet. Okay, that's good, but apparently there were some studies that were done, and it also have an impact on the hydrological cycle. In some region, you could cause drought or then flooding or something. It's a very complex system. We don't fully understand it. To start to mess up with those kind of system, I personally think is not the avenue that we want to pursue. So these are basically or you could seed cloud in the stratosphere, just like volcanic eruption does. You can actually inject sulfate aerosol in the stratosphere and artificially create those clouds that volcanic eruption creates. And I will end with this. Going into the future, new governance, maintain the Arctic for global health. Arctic as a test bed, this is my first argument. Similar issues will arise later at lower latitude. There will be water conflict between the north and the south because we think of the tropics becoming drier. Our latitude will become wetter. There will be conflict for water between the north and the south. Sea level, population relocation, you can imagine, like I think in Bangladesh there's 1 million people like living within 1 meter of the sea. 1 million people to relocate. What do you do with those people? Huge border problem, huge relocation. And not just in those countries, but like, I mean, even the US with Florida, if you wait long enough, even in New York, you're gonna have to have like lots of infrastructure to actually compensate for these kind of like measures. So basically we say, well, let's take the Arctic as a test bed. Let's try to see if we can work together and solve this issue, and then learn to work together, can apply these means of working together to a more serious problem, which is what's going to happen at lower latitude if we keep like producing CO2 like what we're doing now. And this is what I wanted to say to you today.